system design. Basically, when you're designing an HPC system, there are multiple components that you need to pay very close attention to so that you can design a balanced system. And it's really important to do these studies ahead of time so that we can come up with the right architecture to fit your needs. Basically, this is how we're going to proceed, talking about the different focus areas that we work on in the lab, looking at the different subsystems, talking about some of the best practices, and then how we apply these to designing end-to-end systems. Basically, we have a large lab in Austin, Texas, dedicated to doing HPC research and development work and coming up with best practices. And in this lab, we evaluate a lot of different technologies, try to understand the applicability of these technologies to HPC and how we can take advantage of those to basically take the performance to the next level. If you think about the different subcomponents that you need to pay attention to, obviously there is the hardware, which consists of processors, memory, your chipset, I/O subsystem, storage, networking, your software stack, like MPI, job schedulers. So they all play a big role in building these HPC systems, and it's important for you to pick the right component. How do I pick the right component is the question that we try to answer in doing these different studies in the lab.
I just need to click this, I think.
Great, thank you. Yeah. So here's one example of a study that we did when I believe this was Sandbridge service first being released. We looked at all the different BIOS options. So if you look at the BIOS on a Sandbridge system, there are multiple options that we can pick that impact performance and also power consumption. Turbo mode, node interleaving, D states, C states. There are quite a few different permutations and combinations of these, and different applications can get impacted differently by these settings. So we basically took up a study and used different applications and benchmarks representing different types of HPC applications. And then we ran those over a 16-node cluster interconnected with InfiniBand, and we basically varied the different BIOS parameters that you see on the left-hand side of the screen over here. This particular chart talks about the turbo mode and what's the impact of enabling turbo mode on system performance, and also what's the impact of enabling turbo mode on power consumption. And different applications obviously give different results. Because turbo mode can take advantage of the power headroom in the system and increase the clock frequency of the processor to take advantage of that. So clock frequency sensitive applications benefit more from turbo mode in terms of performance as opposed to some other applications that may be more I/O bound or memory bandwidth bound. But we also saw that the increase in power consumption was even more than the increase in performance when you have turbo mode on. So that tells us that if you want to optimize for best performance, so it's better to turn turbo mode on. But some of our customers want to optimize for performance per watt because power consumption is very important for them. And in that case, turning off turbo mode would give you better performance per watt. So in this study, this white paper, we actually looked at all the different aspects and created charts similar to this for different BIOS parameters that we focused on. And then try to distill the learnings to different prepackaged BIOS configurations that you can use if you don't know exactly what your application characteristics are. Another study, this focuses on generational comparison between processors. So here you're comparing an Iron Bridge system with an 8-core 2.6 GHz processor to Sandbridge system to an Iron Bridge system, 12-core 2.7 GHz processor, and all the data is normalized with respect to this processor, the Sandbridge processor over here. This is a study that we conducted in collaboration with NTSA and focused more on the manufacturing, computational fluid dynamics, and structural analysis type of applications. And so that, and of course the HPL benchmark is depicted over here. Because since HPL is very sensitive to clock frequency and number of cores, it can take advantage of number of cores that shows the biggest improvement. But for some of the applications, that's not the case. And that's a function of some of the applications being more memory bound, so that increasing number of cores doesn't necessarily benefit those applications. So it's really important to pick the right processor to match the type of applications that you're running. And on the next chart over here, we did a different study. Basically, we looked at the impact of the processor bin within a generation. So these are all high-rich processors. And we looked at different processor models with varying number of cores, varying number of clock frequencies, and of course, varying power consumption levels. And you can see the trends are similar across most of the benchmarks, except for the LS-DYNA over here. And we know that LS-DYNA is very sensitive to memory bandwidth per core. That's part of the reason why, going from the first data point to the next data point, we see an improvement in performance. But after that point on, after basically the 8 core point, we don't see any improvement. Actually, there is even a decrease. And all the data points over here are normalized with respect to this first data point over here. So all the application data is normalized with respect to that first processor. And that's the reason why we see this trend, is because the system is bound for contending for memory. So if you're designing a cluster for this particular application, you may be better off with a processor that has fewer number of cores, but maybe higher clock frequency. Another decision point is performance per watt. So as I mentioned, performance per watt is an important metric that a lot of people look at when designing clusters. In the previous study, while we were doing all these tests on a 32-node cluster, we actually measured the power consumption over the entire cluster while the application is running. And then we took the performance metrics and the power consumption metrics and then plotted performance per watt for those different processors. So higher performance may not always mean best performance per watt. We focus on this specific data point over here. I'll go one slide back to remind what the performance looked like. So obviously, 133 versus 138, the second bar from the right has better performance than the third bar from the right. However, when you look at performance per watt, it's a different story. Basically, this bar here has better performance per watt compared to this bar over here. And that's because of the fact that we're going from a 150 watt processor to a 130 watt processor. It's relatively the same, basically the same core count. Although the clock frequency is going up, for this particular case of Fluent, the gain in performance is not enough to compensate for the increase in power consumption of the processor. Therefore, we see a decrease in performance per watt. But when you go to the next processor, basically with more cores, we are saying improved performance as well as improved performance per watt. So, once we decide on the processor and the number of cores, power consumption level, even the bins that you choose make a difference on the performance level. In this particular study, we examined two different processors, but we vary the type of bins. It's the single rack bins versus dual rack bins. So this shows the percentage of performance drop with single rack bins. So dual rack bins perform better in terms of memory. So this is just running the speed benchmark. But you'll see that some of the memory-intensive use cases had a big difference in performance application level as well. But for something like HDL, which is not necessarily very sensitive to memory bandwidth, there's really no difference here. After we look at CPU, memory, what's in the system, interconnect performance is very critical. One of the studies that we conducted to look at interconnect performance compared InfiniBand to 40 GigE. But for 40 GigE, we tested both RoCE and TCP/IP. And we were using MVAPICH to do this test, so it was very, very easy to switch between interconnects. On this particular cluster, we had the error correction turned on these nodes, so you can see the latency level higher than some other studies that you've seen. But if you look at the micro benchmarks, obviously there is a difference, latency difference between InfiniBand and RoCE, but also a bandwidth difference because InfiniBand APR is running at 56 gigabits per second versus RoCE at 40 gigabits per second. But how does this translate to applications? So I mean, it's always good to look at the benchmarks, micro benchmarks at a node-to-node level, but we also need to understand how those benchmarks translate to application level performance. And to understand that, we set up a 32-node cluster. We use the Mellanox Connect X3 cards, which allow us to use InfiniBand FDR and RoCE on the same hardware platform. And then, as I said, use MVAPICH 2 for these different applications. On these charts, you'll see the number of nodes followed by number of processes. So these were 10 core processors, 2 processors per node, therefore 20 cores per node total. And all the runs were fully subscribed runs. So you'll see the data points for 1 node, 20 cores, 2 nodes, 40 cores, all the way up to 32 processes, sorry, 32 nodes, 640 cores. The first graph shows WinPack. We have FDR, 40 GigE with RoCE, 40 GigE with TCP. And as you can see, all the way up to 32 nodes, there wasn't a lot of difference between the different interconnects, different targets used. You'll start to see a slight drop-off in performance with 8 nodes using TCP. But at the end, they are in the same ballpark all the way up to 32 nodes. If you look at mass parallel benchmarks, LU, the story is a little different. RoCE and FDR keep on par all the way to the 32 nodes. And as you'll see, all the data points are normalized with respect to InfiniBand over here. So the data point is normalized with respect to InfiniBand to see how much drop-off is with different number of nodes. But clearly, even at 4 nodes, TCP/IP over 40 GigE starts dropping off. At the 32 node level, very sharp drop off for TCP/IP over 40 GigE. But RoCE over 40 GigE were still pretty low for this particular application.
What are the 40 GigE adapters here?
They're all Mellanox Connect Stick 3 adapters. So we took a 32 node system with dual socket fiber bridge and put Connect X3 adapters in them. All we did was using MVAPICH 2, well, we have to change the firmware on the adapters as well, to switch between InfiniBand to 40 GigE to 40 GigE RoCE. But using MVAPICH 2, we ran the same applications on 3 different transports.
So the 40 GigE TCP is basically IP over IP.
No, it's IP over 40 GigE Ethernet. TCP IP over 40 GigE Ethernet. So there's no IP over IP in these charts. That could be another data point. We have FDR with native InfiniBand. We have 40 GigE RoCE with RDMA over 40 GigE. And then we have the green bar, which is 40 GigE TCP, which is traditional TCP IP over 40 GigE, no RDMA involved. And the situation changes as we add more communication-intensive applications. WRF is a better modeling application. And if you look at the profile, it uses a lot of broadcast messages. So it becomes communications heavy as you increase the number of nodes. And you'll see that more larger messages or more data is exchanged between the nodes as you increase the cluster size. If you're curious about the performance profile or the MPI profile of these applications, I highly recommend taking a look at the HPC Advisory Council website. And at that website, you will see different profiling cases for these applications, and you can see how many messages are exchanged, how they change by node count, and how it gets impacted when you change MPI parameters. But as I said earlier, it uses a lot of all-to-all, and you can clearly see that even 40 dB Rocky starts dropping off, starting with 8 nodes, and clearly TCP is not holding up. When you use MILC does a lot of neighbor communications, but it's also very communications heavy. Does non-blocking sends and non-blocking receives, and as you keep increasing the number of nodes, the size of the messages increases considerably. You'll see basically 40 dB Rocky dropping even at 4 nodes, and significantly drops off when we go to 32 nodes. So, in conclusion, some of the results on Rocky look pretty promising. It really is a matter of application that you're using and the communications pattern. Even on some of the applications we've seen, Rocky starting to drop off at 8 nodes. But if you don't need necessarily the low latency, the highest throughput level of InfiniBand, we've seen some of the users using 40 dB for I/O, for example, being able to access cluster for their I/O subsystems. So that's also a good alternative that's out there available. But there are some other requirements around 40 dB Rocky, such as needing data center bridging technologies on the switching side, so that the Ethernet parity becomes lossless. But TCP/IP pretty much stops scaling up to 4 to 8 nodes. So unless you have embarrassing parallel applications or applications that don't do a lot of message passing, then TCP is not a good option for inter-process communications. The other aspect of designing systems, as we've heard today, a lot of the systems are deployed with accelerators today. Some systems are more homogeneous in terms of accelerator usage. Some systems are more heterogeneous in that they have few nodes that are accelerator capable and more nodes with the CPU. So that's an area that we also spend a lot of time in. We do application studies with GPUs, with CO5. We look at different accelerator technologies out there, such as FPGA, and try to share the best practices with the HPC community to help them configure the right accelerator optimized servers for their environment. In this particular study, we were looking at the performance difference between NVIDIA K20s and NVIDIA K40s. This was on an R720 Dell PowerEdge R720 system that takes 2 NVIDIA GPUs or 2 Xeon Phis internally, comparing the CPU to CPU plus GPU configurations using the LINPACK benchmark. And with K20s, we were seeing 5.2x performance, 5.1x performance. And with K40s, we were seeing up to 6.2x performance. One of the biggest advantages of K40s is that it has higher memory, so it allows you to run more applications that are more data intensive or require large space for data. But not only performance, as I mentioned, but we also looked at the performance per watt. If you look at the overall performance per watt, it remains similar. There is an increase in performance per watt, although the power consumption remained relatively the same since the performance went up. Performance per watt also went up, and we're continually seeing this trend as our partners release new technologies. We see an increasing trend in performance per watt. And I think this is if you're keeping count, This is probably the fourth time that you're seeing this slide. Sorry about that. But the difference is that we actually ran this study in the lab. So this data is from the HPC lab that we have. After seeing 3 presentations with similar graphs, I thought about, hey, should I remove this from the presentation? But I wanted to make this point that having multiple presentations talk about this technology and this data is probably proof that this is very important, very critical. You can design the fastest cluster you want. You can get the fastest server platform, equip it with the fastest CPUs, the best network interconnect, the best accelerator that's out in the market. But unless you have the right tools, right software stack, and the right middleware to take advantage of that, you can't necessarily unleash the performance of the system without proper optimization. And I think that's why you're seeing this slide over and over. It speaks to the importance of the work that's being done over here, and MVAPICH deserves a big thank you for that. And then lastly, what we try to do is we try to apply all these learnings to domain-specific solutions. So once we understand how a specific application or a specific set of applications behave, we want to be able to design systems that are targeted towards those applications. This particular example is a genomic analysis platform that we released last year that has a compute platform at the bottom. And this compute platform uses the highly rich EN processor. So EN is the processor that has fewer memory channels. It's not the highest end EP processor. But we found out that EN works very well for genomics applications because it gives us the best performance per watt. And this platform happens to give us the best performance per use space, so best density. So we went with these blades that have basically 32 servers in 10 use space. On top of that, we had a Lustre environment. This is the product that we collaborate with Veriscale on, the Dell Veriscale Lustre environments, which provides scratch space for this solution. On top of it, we have an NFS configuration, which is also a highly tuned NFS configuration that we work with on as the XFS bus in the back. On top of it, we have a path node that provides large memory space for your applications that need that large assembly kind of environment, up to 1.5 terabyte memory. And then on top of that, you have 2 login nodes, 2 head nodes, 1 node for the Lustre management, and then 1 CIFS gateway. Because all these genomic appliances output their data using the CIFS protocol, so you need a CIFS gateway to be able to put that data directly onto your Lustre file system. So the data comes in through the CIFS gateway, lands over the Lustre file system. The compute node work on that data, and then your NFS can host your own directories or stuff that you want to keep for a longer period of time. And then this entire configuration ships from the factory rack stack, all the software installed. When we did the performance analysis of this platform, we focused on genomics workloads and basically wrote a white paper describing how many genomes you can analyze on this system, how many genomes you can analyze per day, and how much power does it take to analyze that many genomes. So genomes per watt and genomes per day were the metrics that we used in performance modeling of this. And basically, doing all that study allows us to be able to build these systems for specific purposes. This was one example, but we have others coming in the pipe targeting other segments as well. Basically, lastly, I want to finish off with some of the other areas that we are looking at. And I believe that these areas are very ripe for industry and research collaboration. Deployment tools, it's important to make sure we can deploy these large systems and maintain them efficiently. Use of virtualization and cloud. So we're looking at how can we take advantage of OpenStack for HPC. And I think some of the MVAPICH SRIOV work that's going on is very interesting in that area. That's why I was asking about the Linux containers, because I think Linux containers really removes that virtualization overhead, but provide some of the benefits of virtualization. So that's an area that I think we can work on. Hadoop, and I listed Hadoop, but I should have said, big data, because Hadoop is not the only big data term, big data technology. There are other technologies, techniques being used in big data. But how can we marry HPC and big data technologies? Hadoop is one specific example. If I have a HPC cluster and a Hadoop cluster, how can I combine them to make sure I can deploy and monitor them from a single interface, that I can submit my jobs from a single interface, and then I can take advantage of things like InfiniBand if I have that in the infrastructure. And how do I optimize the data movement between the Hadoop side and the HPC side so that you don't have to copy data over manually from one side to the other. Cluster file system and parallel file systems in general is an area that we need to do a lot of work on, and I think some of the talks today touched on the topic. One example is how can we take advantage of SSD technology for parallel file systems, and what are the benefits, and what can we do to optimize performance with price of SSDs and spinning media. And then accelerators. There are a lot of emerging trends, use of FPGAs. Our friends at Intel and NVIDIA coming out with new accelerators. How can we take better advantage of these in HPC? How can we enable heterogeneous computing better? These are all some of the focus areas that we have internally in our lab as well. And we have a website that we basically publish the results of these studies called hpc@dell.com. So feel free to look at that website and share us your questions and concerns. We're very open to collaborating, and we share our results openly with the HPC community so that everybody can take advantage of those. That's all I had. Thank you.
Okay, so let's any questions?
I have one question. Is there any particular reason